C, I don't know, C, whatever. I will use C here later on for something else. These are constant vectors. So some constants, okay? And obviously you can relate these constants to the initial condition, because if x is 0 is phi of 0 to c, so c is phi inverse times x is 0. So actually I can write x of t as phi of t multiplying with the c's, and the c's are phi of 0 inverse times x of 0. And this 0 actually can be anything, it doesn't necessarily have to be 0, so this can be any tau, any tau. So in other words, it relates the solution at previous time tau to the solution at this time t, so this is why we call it state transition, right? For LTI, this is the e to the at. Here we don't have e to the at kind of thing. It's not e to the at anymore. Actually, we don't have an analytical form for it. So it's just, we know that it just exists. And we know how to construct it numerically using simulations, but there is no analytical form for it, for the state transition matrix. So this actually encourages to define a normalization for it. So the normalized phi, obviously, we'll take it as this guy to be identity, okay? So now on x of t is just phi of t times x initial. So it's a matrix that takes your initial condition, gives you the solution at time t. Very good, okay? Okay, we're very familiar with this concept, and I'm reminding you of the last fact. It was a theorem in linear systems theory that phi is a fundamental matrix of 1. Delta of t is its determinant. Then delta of t satisfies this equation. It's delta of 0 e to the 0t, the integral of the trace of a of s ds. And again, this 0 can be any time. This 0 and this 0 can be any time tau. So in particular, you may write this differential equation for the determinant is delta times the trace, delta of t times the trace a of t. So what you're trying to say here is that if delta of 0 is not 0, delta is the determinant, okay? And the matrix initially, its identity or any independent, comprised of any independent vectors. So the determinant, of course, is not 0. The initial determinant is not 0, and we might worry that as we simulate on the matrix loses its rank. But this equation says that this will not happen, right? Because this guy is not 0, the exponential will never be 0. So if delta 0 is not, then delta at any time is also not, which means that phi is indeed non-singular for all time. Okay? Any question about that? So we're done with the revision, the quick review of what we should know about the fundamental matrix. Any question about that? And here we're trying to develop a theorem for the stability of time periodic systems. I will show you, we will need this lemma, and it's still for anything I said so far is not confined to time periodic systems. So the concept of state transition matrix or the fundamental matrix, this whole thing, the concept of fundamental matrix is for any a of t, not necessarily time period. Any time varying linear system will have these properties. And also this lemma for any time varying system, not necessarily time periodic. So if I have phi and psi, they are fundamental matrices of our system 1. Then they are related by a constant matrix. There exists a constant, this is very important, constant matrix C such that, you know, 1 is equal to the other times C. This is for all time. This is very interesting because it's for all time. This is at any time, at any time. So at any time they are related by the same matrix. Okay? So that's interesting. And we can do the proof very easily. So, okay, show me that such a matrix exists. Well, there is a very intuitive definition for it. It's phi inverse times epsilon. Right? So define C, the candidate C is phi inverse at any time times epsilon at that time. It's very legitimate. Actually, the lemma says a constant non-singular. Obviously, it's non-singular because I can invert any of these because we just proved that, or we just stated the theorem. But the issue is that it's really interesting that whenever you do that for any time, it gives you the same metric. So I need to show that C is constant. So I will compute C dot. So this is phi inverse epsilon dot plus d by dt of this inverse matrix times epsilon. Okay? So phi inverse, that's fine. If C dot, because it's fundamental matrix, I have a formula for it, right? Which is what? If C dot. What will be if C dot? It's just A if C, right? Because it's fundamental matrix by definition. Plus the derivative of an inverse of a matrix. This guy is just phi inverse, phi dot, phi inverse, and we have negative. This is times if C. And again, phi dot is just A times phi, right? So what we have here, let's recap here, phi inverse A epsilon minus phi inverse A phi inverse epsilon. So obviously these guys go, and then you have two equal things. So this is indeed 0, C dot is 0, so C is constant. That's cool. So you need two fundamental matrices, they are related by constant matrix. Okay? Now we are about to state the main theorem. And it's very easy actually, and very, very useful. It is the only theorem out there for linear time periodic, and it's necessarily sufficient. You don't need anything more. So now we need to confine two time periodic systems. So here I define my system 1, so I'll define time periodic x dot equals a of t times x of t, and a of t plus large T is just a of t. So a is periodic, and I will call the system 1 periodic. So I have system 1 that is general and system 1 periodic. Okay? So this is a special case of the general thing. Now we state the theorem here. So this is a theorem which is known as Floquet theorem, sometimes called Floquet decomposition. Okay, what does it say? Phi is a fundamental matrix of phi of t is a fundamental matrix of this system, the periodic. Then phi of t plus t is also a fundamental matrix. Remember, phi of t, the solution of a periodic system, is not necessarily periodic for sure. May diverge, may converge to origin, may keep orbiting, so it's not periodic. So this guy is saying that phi of t plus large t is also a fundamental matrix. This is easy, but we will need it for the second part. The second part is the meat. So there exists a periodic, non-singular matrix P of t, and a constant matrix R of R, of t of course, such that you can decompose your flow, your state transition or whatever, as P of t e to the r t. We'll prove the theorem and see later on why this is so important and what was the implication. Okay? Any question? So let's prove part 1 is so easy. This is the proof. So what's the given? The only given here is just phi is a fundamental matrix, right? So we'll start with the given and try to reach this guy. So phi is a fundamental matrix. It means what? It means that it satisfies the differential equation. So phi dot at any time is A at the same time, phi at the same time, right? In particular, I will choose the time to be this guy. Again, this has to be the same time, and this is the same time, right? But A is periodic, right? So this simply gives you that phi dot t plus t is A of t, phi of t plus t. And that's it, right? Because we showed that this matrix, whatever its name, satisfies the differential equation. So this matrix is a fundamental matrix. So phi t plus t is a fundamental matrix. Any question about that? That's so easy. But we will need it in part 2. So you just proved that phi is a fundamental matrix, and we know